All right, so now the electric field. The field concept is used to answer the question or resolve the problem of action at a distance. So how is it possible that there is a gravitational force um, between two masses when the two masses aren't touching each other? Likewise, how is it possible to have an electric force between two charges when the two charges aren't touching each other? Okay, so the answer, of course, is a field. Mass will affect the space around it, creating a gravity field, gravitational field. Likewise, charge will affect the space around it, creating an electric field. So I guess we could visualize the field as being just, some sort of effect here in space. And both the mass affects the space around it and the charge affects the space around it. Now, if we put another mass or charge in that field then, so down here, if we put another mass here, then it will experience a force because it touches the field. Likewise, if we put a little charge Q here, then it will experience a force because it touches the field. Now that some slight difference between electromagnetism and gravity is that electric force could attract, but it could also repel. Now, we know that the gravitational force is given by an inverse square law. And likewise, the electric force is also given by an inverse square law, which is Coulomb's law. Now, with gravitation, we identify these first three terms here as being the gravitational field, because then the force of gravity is little m times g. So this is the gravity field. We'll do exactly the same thing with electric field, where we take these first three terms here, kq over r squared, as being the electric field. Now, if that bit is electric field, then we see that a force is little q times the electric field, or alternatively, the electric field is a force per unit charge, and it therefore has units of newtons per coulomb. Now, K is the same electricity constant that it was before. Whoops. Can I shrink that? Let's see, can it be shrunk? Yes, it can be shrunk. Oh, that's much nicer. There we go. So K is the same electricity constant, 9 times 10 to the 9 meters squared per coulomb squared. Q is the charge creating the field, and D, or I guess I should call it R now, R is the distance from that charge to the field point. Now, the electric field direction, electric field is a vector quantity, and its direction is the direction that a small imaginary positive test charge would go. So a little positive test charge would be repelled no matter where you put it around this positive. So this positive charge is a real charge. These are just test charges. So the field goes away from a positive charge. If we have a negative charge, and we want to find the electric field up here, we put a little positive test charge. That positive test charge will be attracted. So the electric field is everywhere towards a minus. All right? So electric field is away from a positive charge, and it's towards a minus charge. We'll skip this. Now, a series of examples on electric field. First, if we consider the electric field in between these two positive charges, so we've got a positive 1 microcoulomb here, a positive 2 microcoulomb here. If we plunk ourselves down here somewhere in the middle, then electric field is away from a positive charge. So this electric field will be away, that's to the right. That's the electric field of the 1 microcoulomb. At this point, the electric field is away from the 2 microcoulomb, so that goes to the left. So 1 to the left, 1 to the right. The electric field will be 0 if those two fields, if those field vectors cancel. Now, in order to cancel, they actually have to be opposite. And we can see that they are opposite at this location. And also, they have to be equal in magnitude. So that's the condition that's required for the electric field to vanish. So we see that they're opposite. The condition that they're equal in magnitude means that kq over r squared is equal for both of them. So the field of this charge is going to be k times 1 microcoulomb over this distance. Now we see on our diagram over here that this distance is x. So that's how far we are from the 1 microcoulomb. For this, it's going to be k times 2 microcoulombs over this distance, because the total distance is 2 meters. This distance here is going to be 2 minus x. Note that this is incorrect in the text. This should be 2 minus x and not x minus 2. So this is the equation that says they have equal magnitudes, and we want to solve that for x. Now, it makes our life quite a bit easier if we just cancel the k out on both sides and just cancel out the microcoulomb units, because then we get a much cleaner looking equation like this. This is just a quadratic. So what we're going to do is we'll cross multiply up these terms, and then we have to expand, and then we have to gather like terms. Now, we should be pretty good at doing this now. This side's going to give us an x squared, so it comes over. There's only one x squared left. This will be minus 4x. It comes over as plus 4x. This will be 4. It comes over as minus 4. This equation, unfortunately, doesn't factor, so we use the quadratic equation. Negative b plus or minus b squared minus 4ac, that's 16 plus 16, that's 32, all over 2a. This is 4 root 2. Cancel out the 2, and you get negative 2 plus or minus 2 root 2, I think. Indeed. Now, we will reject the negative, because as defined, x is positive. So we've got negative 2 plus 2 root 2. Root 2 is about 1.4, so this is about 2.8. Subtract 2, it's about 0.8, and these are units of meters. Looks like that went in the wrong place. That should go right in here. Okay, so there's our solution then to that first example. Okay, next example. We want to find the electric field at a field point x. This will involve, again, a couple of electric field vectors, and we need to add these electric field vectors together to get the resultant field. So here we are here, and we've got two 1 microcoulomb charges, and our field point is at x right here. So there's going to be two electric fields at this point. Now, I can't draw on top of this, unfortunately, so I'm going to have to redraw it over here, but you can just draw on top of your diagram. So here's the field point x. So electric field is away from a positive, so the first one, I guess we'll call it E1, goes that way. And electric field is towards a negative. So the second field, I guess we'll call it E2, goes this way. Now, we've got lots of symmetry here. It's the same charge, and it's the same 3-4 geometry. So we expect that these two will have the same magnitude because of that. Now, in order to calculate that, we're going to have to do kq over r squared. For r, we've got to get the distance from the charge to the field point. Well, this is a 3-4, and therefore 5 triangle. So r is actually going to be 5. So we've got 9 times 10 to the 9, 1 microcoulomb, and we're dividing by 5 squared. That works out to be 360 newtons per coulomb for both of them. Now, this is E1, E2 will be the same magnitude. We need to think next about direction. Oh, I suppose I should say that just like electric force, electric field has an absolute value in it. Let's go back here and put that absolute value in, because the minus doesn't have any physical significance. Okay, so put absolute values here and also here, okay? Because these things have to be positive numbers. Back to our example then. And so now we want to add the vectors. That means we need to know what the angle is. This angle theta here will be the same as this one and the same as this one. Now in a 3, 4, 5 triangle, this is 4, this is 3. Well, you could just work it out. It's going to be the arctan. It'll be the arctan of 4 over 3. And in a 4, 3, 5 triangle, the angles are 53.1 degrees and 36.9. So there you go. Now, well, let's just send that to give myself some more workspace. Clear it. Now we just want to add the two vectors. We see with horizontal being the x-axis that the horizontal components are going to cancel, and we're just going to be left with the vertical components. So we'll just set up a chart there for that vector addition. So, well, we'll draw it again here like this. So there is what we're calling the second electric field, and here is what I call the first electric field, and this angle here was theta, and that was 53.1 degrees. So in the x direction, and in the y direction, so first of all, electric field 1 is going to be in the x direction, it's going to be 360 cos theta, and then it's going to be downwards 360 sine theta. The second electric field to the left is going to have a negative x component, and it's also downwards, so it'll have a negative y component. So my resultant field then, the sum of these electric field vectors, is going to be 0 in the I direction or horizontally, and then it's going to be downwards 720 sine of theta in the j direction, and the sine of 53 degrees is 0.8. It's 4/5 or 0.8. And so that's 8 times 72, which is 6 carry a 1. That's 576 negative j. And that'll be in units of newtons per coulomb. So that's the resultant electric field at that point x. And this should be a familiar process of adding vectors. We're not going to spend a whole lot of time reviewing that. So we found the electric field at the point x. Now for this next problem, you want to find the electric field at the origin due to these two charges. You'll again have to add two vectors. There's a little bit more work involved here. I'm going to suggest that you stop the video, try doing this problem on your own in pencil, and then when you're finished, you can play through the rest of this video for a solution. Okay, so hopefully you started by drawing an electric field diagram, because we've got a positive charge and a negative charge. Our field point is up here. So field is going to be away from this positive charge. Let's call that E1 for field of the 1. And then it'll be toward this negative charge. Let's call that E4. Now we need to compute those two fields. The electric field 1 is KQ over R squared. That's 9 times 10 to the 9. It's a 1 microcoulomb charge. 1 times 10 to the minus 6. And the distance is given as 1.2 meters. So if we compute that, we find it's 6250 newtons per coulomb, and it's straight up in the positive j direction. Now, for the field of the minus 4 microcoulomb, it's again going to be KQ over R squared. It's going to be on an angle, and we need to know what R is. Now, we're told that this distance is 1.2, and this distance here is 2.5, so the R distance is just this hypotenuse here. So the distance R, well, I guess we could draw it here on this for clarity. So this is 1.2, this is 2.5. So this is the hypotenuse, and that works out to be 2.773. Now we're also interested in what this angle is, and we may as well work that out while we're at it. This theta will be the arctan. That says equals, believe it or not. Arctan of 2.5 over 1.2. And so what's that angle? It's 1.12 rads. or if you work in degrees, it's 64.4 degrees. Okay, so we compute the field now. It's 9 times 10 to the 9, 4 microcoulombs, and we divide by 2.773 all squared. Magnitude-wise, that gives us 4681 newtons per coulomb. And what we need to do now is to add those two vectors. So there's our vector chart. There's the calculation of the first field magnitude. There's the calculation of the second field magnitude. Okay, so now add the vectors using a chart. So x component and y component. Okay, so for the first vector, it's easy because there's no x component, and it's just 6250 upwards in the j direction. For the field of the 4, it's going to be, with this defined as theta, the x component is going to be positive sine theta. So positive 4681 sine theta. And the y component is going to be a negative cos theta component. So putting in the angle theta of 1.12 rads, we get the following resultants. 4221 in the I direction, and this gives us 4224 in the j direction, newtons per coulomb. So that is the resultant field at that field point. So those are the I and j, x and y components. If you convert that to a resultant by squaring the I, squaring the j, adding them together and taking a square root, you get 5972 newtons per coulomb. And at an angle of about 0.79 rads, or 45 degrees in this direction. So even though E4 has got a downwards negative y component, E1 is so large that the resulting field ends up pointing in this direction at around 45 degrees. So that's our lesson on electric field.